Hello, welcome to lecture 24 in our series, and today we're continuing with the quantization of gauge fields. Right, so last video I introduced gauge fields as these spin 1 representations of the Lorentz group, with the caveat that these representations, they have their Lorentz vector, so they have 4 degrees of freedom, but in nature we have less physical degrees of freedom, right? And we build this theory with these 4 degrees of freedom by introducing gauge symmetry, which is really a redundancy, right? You're using more degrees of freedom than necessary in your Lagrangian, in your formalism, right? Because it allows you to keep explicit Lorentz invariance and prove renormalization and other very important properties. But in fact, at some point, you need to fix the gauge or put some, which is equivalent to putting some constraint to bring down the degrees of freedom to the physical ones, right? And I have shown at least 2 ways of doing that, right? We looked at the physical gauge, where you really have only 2 degrees of freedom from the start, right? And I showed also the covariant gauge, where you have to you allow for the non-physical polarizations to stick around, but you impose a condition, the Gupta-Bloiler condition, that effectively constrains the kind of states that you can have in your theory, so that the unphysical polarizations never contribute to observables, right? So what we're doing today is doing this now in the path integral formula, right? So you see that this is advantageous from many points of view, right? It's easier to understand how you put in constraints. It's easier to understand how the constraints are going to the path integral, and it's also much easier to generalize for the non-abelian gauge theories, which we'll see down the line, right? So let's get on to it. I'll follow the usual thing we have been doing for path integral, right? Which is very similar to what we did for the scalar field in this case, which is first I'll go to Euclidean, do the Gaussian integrals there, because I know there's no subtleties with the inversion of operators in the Euclidean space, and then I'll come back to Minkowski. Right? So the first thing would be to do Wick's rotation. Right? We know how to do that for the time component of the position, right? Which is just, now I'll call it like that. So the Euclidean time will be x4, and of course in Euclidean space doesn't matter if it's up or down, right? In the case of the metric I'm using, which is plus minus 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 metric, right? The diagonal of the metric. The same is true for the 0 component. I also know how to work with the derivative in time, right? This is just del x0, which will be I del x4 or I del 4, right? Consistently with this one. I have to decide now, what do I do with the time component of the vector field? Remember, the vector field is also a 4 vector, right? So it needs to rotate too. In terms of dimensions, right? The field has dimension of energy, right? Which is like the derivative and not like the time component, right? So based on dimensions, you see that the field must transform like energy, right? It has dimensions of energy and not 1 over energy, which is the dimension of time. Also, we know that this guy, right, transforms in this way. So it needs to rotate in the same way the derivative does. And that's why I'll define an A4 that will be just given by this equation, right? It's transforming just like the derivative. Now I can look and see how F mu transforms, right? So the electric field in Minkowski, let's use M here to indicate Minkowski, is just this component of F mu, right, which is del 0 AI minus del I A0, and I can use these expressions here to rotate it. So from the derivative I get an I, and I can write this in terms of del 4, right, AI, and in this other expression I use this, right, so it's I del I A4, which is the same as IF4I, which I define as the Euclidean I times the Euclidean electric field, right? And of course, using these, I can write that F0I is minus IF4I. All you have to do is do the same with the indexes up, right? Now, for the Lagrangian, what I have is the Lagrangian in Minkowski is given by minus 1 over 4 F mu nu, right? Let me write this in terms of the components, F0I, F0I minus 1/4 of Fij, Fij, right? And then this is just using these two relations, right? This one and this one, this part and this part, right? I can substitute both here. You get just minus 1/4 F4I, F4I minus 1/4 Fij, Fij, which now I can put together in terms of the Euclidean sum, which is the same, right? In this case, nothing changed. Mu Euclidean, F Euclidean mu. And that means that if I go back, right, to the exponential of I times the action, right, I don't need the exponential, let me write just I times the action will be I integral on d4x of this, which will be the same. Now, this d4x will become minus I that comes from the time component, d4x Euclidean, right? Minus I gets together with the other one outside here and just disappears. So I got just the d4x Euclidean, right? And this Minkowski Lagrangian becomes just minus 1/4, right? Using this expression, F mu Euclidean, F Euclidean Ij, and then I just have to bring this minus outside, write these as d4x Euclidean, F mu Euclidean square, which is what I call the Euclidean Lagrangian. EM means electromagnetic, right? And this is what I call the Euclidean action. So the exchange in the exponential, I times the action for minus the action, right? That much is clear and easy, right? You can also see pretty easily that the electromagnetic Lagrangian density is just 1/4 F mean U Euclidean, F mean U Euclidean, which is just half of the sum of EI Euclidean square plus BI, the magnetic field in the Euclidean space, square, right? Which is the usual thing for Euclidean space Lagrangian, right? Or just essentially the energy. I'll stop writing this Euclidean index from now on, so it's implied that everything is Euclidean, and I can do an integration by parts at this step, right here, to rewrite the action, right? So as d for x of minus a mu delta mu del square minus del mu acting on a mu, right? So I just did the integration by parts to put the operator in the middle between these two fields, right? And there's no subtleties in that, because again I have periodic boundary conditions for the path integral, right? So now the idea is to obtain a functional generator by doing this integral, right? This path integral of minus that action. Well, qualitatively speaking, right, this path integral has two different kinds of configurations of this field being summed over in here, right? I could think that I'm taking different configurations of the field in space-time, and if I take a configuration a mu prime and another one which is a mu prime prime, right, I can think of the terms in the sum where this is true. Alright, let's put minus 1 e del mu lambda. So there's no lambda that makes this guy equal to that one by a gauge transformation, right? So this is really a sum over different, I mean inequivalent field configurations, right? But there's also, for each of these guys, there's also another sum going on. Let's say take a mu prime, right? I'm also summing over other fields which are just a mu prime plus a gauge transformation, right? They are physically equivalent to a mu prime. And that sum is also an integral, because I can just vary lambda, which is a function, continuously, and I'll get a whole family of fields which are equivalent to this one, right? So each of them is equivalent, right? And I would like to separate these two. That will be my general strategy. So what I want to do next, right, is to find a way to take this path integral and separate it in two parts. I'll have an integral over fields. I'll call this the gauge fixed one. That means I'm just summing over fields for a fixed value of lambda. I cannot vary lambda in here. And then I have an integral over all the different values of lambda, right? Also a path integral over all the forms of lambda, right? And then of course I have the integrand, right? Whatever is here is equivalently here too. If I can do that, let's suppose, right, that's my aim, right? If I can do that, then this thing has become a multiplicative factor, right? Because this is essentially the volume of this internal space created by the U1 symmetry. Still thinking about the non-abelian case, the abelian case here, right? This is essentially the volume of this internal symmetry, right? The internal space of functions. And if I can do that, then I know that in any observable I'll be also dividing by a same path integral, so this guy goes away, right? So that's our aim. We want to find a mathematically rigorous way of separating this sum over the inequivalent physical configurations and the sum over the configurations that are all physically equivalent, right? So the first thing I want to do to make this more formal and more generalizable to the non-abelian case is to use a gauge fixing which is a bit more general than the covariant one, right? So I use this condition, right? I mean the Euclidean, so that's why I don't care about the indexes being up or down, but you could write it any way you like. And the conditions we were using before are included here because I just have to take this c function equals 0, right? And now I have a c of x that can be anything. And I'll keep that general in this way, and then I can choose different gauge fixings by choosing different c's. I will see. Now I want to define, to make our problem more defined, something called the orbit of a field configuration A. So let's take, I don't know, 3 different configurations, right? And let's think about all the other configurations which are just given by one of these, say A mu prime prime. I don't know, it's just take all the configurations which are given by these for some lambda, right? This, the set of all configurations which are related to A mu prime prime by some gauge transformation, I call the orbit of A prime prime, right? And then I can define this orbit for the other guys, right? So this set is the orbit of A, and this guy is the orbit A prime and orbit of A, right? And this, if these orbits don't cross, these guys are really inequivalent, right? There's no gauge transformation that takes one into the other. Now, what is a gauge fixing condition, right? Assuming this is a good fixing condition, what it should do is, if I go to the space or where all these orbits live, this is an internal space, right, for the field. It's not space-time, right? But if I go to that space, a gauge fixing condition, a good one, will be a plane, right? Let me try to draw this. That only crosses each of these orbits once, right? So it selects just one field for each of these orbits, right? This is a good gauge fixing condition. Let's call this gauge fixing 1, right? And you can have others, right? You can have a second gauge fixing condition. And the second one does the same for a different value of the fields, right? It's a different configuration, but still connected, right? This is fairly doable in the abelian theories, right? It's very hard to do in the non-abelian ones. So if you're curious to see how complicated it can be to actually get just one crossing for each orbit in the non-abelian case, go and look for Gribov copies, right? But we'll restrict ourselves to the abelian case for now and see how far can we go, right? So a gauge fixing is essentially finding one of these planes that crosses every orbit once. And this integral over lambda is essentially the volume I get from the integration of all these different planes, right? This is the integral I want to factor out, right? Let's start by parameterizing the orbits, right? So I can write an orbit by making a gauge transformation, take one of these fields, right? And gauge transform it to, I'll use this formation, A mu x chi, right? So I'll put a chi here, which is the parameter of my gauge transformation. Del mu chi of x. So chi of x is what I was calling lambda before. I want to differentiate from lambda because this guy will be integrated over, and so I want to, we use lambda for a bunch of other stuff, so I prefer to use a different letter, right? But essentially, this is any point in a particular orbit that I can get starting from a mu of x, right? And then I can also write the value, I'll define, right? So this is what defines this a mu of chi. And I can also define the value of chi that puts me in a particular gauge fixing. I'll call this chi a of x, and this is the guy that satisfies this condition, that the second derivative of chi a of x is minus del mu a mu of x plus c of x, right? It's easy to see that if I take this guy and substitute here, right? Let's say I'm calculating now a mu of x of chi of a, right? I'm using this chi of a here. If I take del mu a mu of that, right? Just looking at the right side here, I'll have del mu. I'll have del mu a mu of x plus del mu chi a of x, and then this is what is here, right? I can substitute, and this minus del mu a will cancel with this guy, and this is just c of x, right? So this is the particular value of chi that puts me in the plane for this gauge fixing. So I use these two variables. Now, what I want to prove is the following identity, right? Suppose I do a bunch of integrals, right? This will become a path integral over d chi of x. So I'm taking all points in space, right? This x becomes to four-dimensional space-time, right? Remember, I'm Euclidean here, right? So I'm taking for each point in space an integral in the value of chi at that point, right? I'm not doing the discretization, but you can get the feeling here, right? The spirit, right? And the same for y, right? So for every position in space-time, in Euclidean space-time, I'm putting a Dirac delta function of minus del mu a chi mu y plus c of y, right? So there's a lot of Dirac deltas, one for each of those integrals, right? And I have a dependence on chi in here, right? This guy is just this one. right? And I'm enforcing that this is equal to C at every point in space, right? And I want to prove that this is the same as 1 over the determinant of the minus derivative square operator, right? So that's what I want to prove. It's important to have some understanding of what we're trying to prove and why, right? So the reason I want to prove that is that if this is true, then I can throw this determinant over here and have an identity which is determinant of this operator, right, times this thing here. Let me copy it. And this thing is just a path integral in chi. And this one is what I can call a functional Dirac delta, right? Because it will point by point in space-time, right? Point by point in space-time, enforce that this function is equal to C, right? And this will enforce my gauge fixing condition, right? Integrating for all the possible gauges, right? Which are given by chi. Chi runs over the gauge parameters, right? If I have an identity like that, I can then plug this one, right? This is just the number one, right? I can plug this thing inside my path integral. And then this Dirac delta will enforce the gauge fixing in my path integral, right? That's what I want to do. But I need to prove this that is inside this red box here first. Right? So let's get to that proof. The first thing I want to do is to rewrite this guy here, which I'll name G of A mu chi, right? I want to rewrite it in terms of this guy up here, this chi of A. Right? So I can show that G of A mu chi, right, can be written as, let me just copy it for now, del mu A mu chi plus C. Right? That's everything that's inside this delta, right? But that can be written as, I just have to expand this guy and apply the derivative, right? I take A mu chi, which is here, this guy, and apply the derivative to it, right? So this guy will become just del mu A mu minus, because there's a minus there, right? Minus the second derivative of chi plus C. But now, these I keep here, right? I'll just rewrite this as minus second derivative of chi of x. But these two together, right, del mu A mu plus C, right, is equal, minus del mu A mu plus C is equal to the second derivative of chi A. Right? Mind you, chi A is not the one in the path integral, it's just a constant value, right? Del second derivative of chi A. Right? This is a constant function. This is a function of position, but it is constant. It's the one that puts me in the point of the orbit that crosses the gauge fixing condition for a value of C. Right? And now, if I go back to the identity I want to prove, let me copy the identity. let me start from the left side here. Okay? So now I can go in here and substitute this. This is G, right? This is G by this one. And make a change of variables. Right? I can take this path integral in psi, right? Or take each of the normal integrals in psi of some point x, right? And make the change from x to x minus xa, right? This is a constant, so the integration measure does not change for each point in space or the path integral, right? But what happens here is when I do that, I'll get a plus term just like this one. So I eliminate this from here. This was on y, sorry. So essentially what I'm saying is that after the change in variables, right, I have this thing here, R4 delta of minus second derivative of chi of y, right? Because this is a change by a constant function, if you want to think in terms of integrals, or just a number at each point in space x, right? So I rewrote the left, in this case, the right-hand side of the left-hand side of my identity here in this way. So that's the first step. The second step is noticing the role of this G of a mu here, right? I wrote it in this way, right? In this one, also in this way, right? And you can notice that if I do a derivative G a mu x of y del x of x, right? So this is a functional derivative, right? This will be, say, let's do this in this version of G. It doesn't matter, right? It can be here, it can be here. In any case, none of these other values really depend on chi, right? Only I have this second derivative, which will now act on a Dirac delta of x minus y, because these are different coordinates. And I'll just baptize these as this operator that depends on x and y. So what's happening inside this delta is this operator acting on chi of y, right? This operator here acting on chi of y. The point is that this operator is like a Jacobian for a change of variables, right? Which change of variables? The variables going from chi to G of a mu chi. If you can see that, think about the discrete version. The discrete version is maybe easier to see. What is going on there, I will rewrite this integral here in a discretized version. Right? Let me just put I goes to 1 into n. Right? This is running over all space-time x here. Now I just put an index and discretize this space and use an index to cover the whole thing. And I have integrals for chi of position I, right? And this second set of integrals is the same thing again for a different index. Let's call it j from 1 to n, but it's covering the same space, right? And what's inside that delta is some operator delta ij acting on chi on position j, right? If I write these as vectors, right? Let's read this guy just as a n-dimensional vector chi, right? And then this delta will be just the delta n, right, of delta acting on the vector chi, which is n-dimensional. Right? Now think about the changing variables, right? If I change this integral from chi to some eta, let's call this eta, right? Which is another vector, same size as chi, given by delta chi. Right? That means that the I component of eta is delta ij chi j, right? And the integration interval dn eta will be the Jacobian, right? The determinant of this delta, right? Times dn of chi. That means that the change of variables I have to do here is dn eta over the determinant of delta times the delta function, right? Delta n of eta. And of course, this determinant comes out because itself does not depend on eta, right? And that becomes 1 over determinant of delta, because this is just a Dirac delta integrated all over space. So the equivalent thing up here is to write this integral it's just the continuum limit of the same thing, right? This integral as 1 over the determinant of the operator that is acting here. Because I can just make a change to integrate over eta of y, right? And the Jacobian here will be d eta of x over the determinant of this minus this del square, which is del g del chi. Del g del chi. That's the change of variables I did, and then I do the path integral and get what is here. Right? So I have proven what I wanted, right? I've proven that the left-hand side of this is the same as this one, right? After this change of variables, right? The first one here. And then that this thing down here is this, and I hope I have convinced you in the discrete version, which is much simpler, because you don't get confused with all the functional stuff. But it's the same story, right? You can properly go from one to another, writing limits carefully, and that's the whole idea. Now I could just plug that identity inside the path integral, and I know now that will gauge fix my path integral, right? But in order to actually integrate and see the propagator, I want to take another step, right? I want to see what's the effect of this Dirac delta I'm putting in terms of a Lagrangian term. Can I convert it into a term in the Lagrangian to see physically what is the effect of that? Turns out we can, but for that I need to use one more identity, which I'll write here. Suppose I take some path integral over this function c, right? The c of x that is on the gauge fixing condition, and I write just a Gaussian term for it. Alpha is just any number, right? Just a number. D for x of c squared of x, right? I know this is integrable, right? There's no problem here. This is just a Gaussian integral. So it converges to a finite number, and I can normalize it. And n alpha is whatever normalization. It's just 1 over this integral, right? So this is 1, right? This is just the Gaussian path integral of Gaussian, right? Now I will multiply the two identities, right? This one and the one I proved above, the one I've proven above, right? Which is the determinant minus del square integral over chi delta of g, which I'll write explicitly, right? A mu chi plus c. And all of this is equal to 1 because I'm just multiplying the two identities. Right? Now I can flip things a little bit here and actually use this Dirac delta to do the path integral in C. Right? That's the whole trick. I want to get rid of this delta and get it up here where the action is. Right? This is where I have my actions for the path integrals. Right? So let me do that. I'll bring this integral over here, the normalization, this exponential, right? And once I have integrated in C, right, using this delta, I have to replace C squared by del mu A mu x chi squared, and I have this determinant. And this is an identity, right? I just did the path integral in C using this delta, which gives me this term up here, right? Now let's insert this identity inside the path integral for the field A, right? So let me take any path integral of the exponential of the action of A, and in general I have some operator here, right? Some observable that depends on A. That's basically anything I can calculate in this theory, right? And let's put the identity here. So let me multiply this thing. This is the same as, let me repeat it. I won't fit. Go down one line. That's the same as this. These two expressions are the same. Now what can I do? Well, there's a few interesting things I can do here. The first one is that I can take, and this is very important now. That's a very important point, right? This determinant does not depend on chi, right? Nor it depends on A. So I can bring it all the way out here. Right? And this is where this procedure would change if we had a non-abelian gauge theory, right? When the point where you see that this guy does not depend on A was here, right? Essentially what I have, what I would have instead of the determinant of minus second derivative is that I would have the determinant of del J del chi, right? That's what really would appear in a general case, right? In this case, del G del chi does not depend on A. For non-abelian theories, it will depend on A, and then I have to take some extra steps to deal with this determinant here. But in the case of the abelian one, I'm fine. If you're curious, you can go to my website. There's many places where you find this, but that's pretty easily, because I use the same notation, written in my Quantum Field Theory 2 notes page 80 to 87. I use exactly the same formulas, but then I have to do some other stuff with this determinant, right? For non-abelian is fine. For abelian theories is fine to bring him out here. Same with this normalization, right? That goes straight outside. And let me start to write this, just so I don't forget anything. The determinant comes outside. The normalization comes outside. Let me make them smaller. Right? And then I have this integral, del chi. I have this integral, del a mu, right? And the exponentials, right? All I have is now the exponential, which will have the original action for the field plus a gauge fixing term, which is the same one you must have seen before in other contexts, right? Del mu a mu chi x square. So what I'm seeing here, and the operator, of course, the observable, still here. So now I'm calculating the observable with this new action, right? So you see that the effect of putting the determinant ends up being just a gauge fixing term in the action, right? Let me make this a little bit nicer, right? And here comes the nicest part of it. We have defined, right, a chi as a plus del mu chi. And we can change between these two variables in the path integration just doing gauge transformations, right? I can do it in this direction or in this one, right? Going back to the original origin of the orbit, right? The point is that the action itself is gauge invariant, right? That's why we are discussing all of this in the first place. So I can put or remove a chi here at will, right? Same for any observable, right? Any observable that makes sense in a theory like that must be gauge invariant. Otherwise, I could observe which gauge I mean, right? Which makes no sense. And I will assume, and this is an important assumption, that the integration measure is also gauge invariant, right? This is by no means guaranteed, right? In fact, it is true for most gauge symmetries, but for the very few where this fails, you have anomalies. We're not going to anomaly here, and I know that the U1 symmetry for electromagnetic theory, right, for QED, is not anomalous. So for QED, for the theory we're looking at, for photons, right, this is not anomalous, and so this is true, right? But at this point, it's just an assumption, right, which can be proven. The important point here is that with these three guys invariant, right, I can go back to the expression up here, right, and put a chi or remove a chi from these three guys at will, right? They're the same. But then, if I put chi everywhere, then I can make a change of variables in the integral, really, back to the field without the chi, and remove the chi from the only place where it really matters, right? It's the only place that is not invariant, right? And get this expression, right? Once I do that, this integral out here becomes just a huge volume, right? Because there's nothing that depends on chi here. This is just a number. This one is just a number, right? That multiplies these other two numbers here, by the way, right? And we know that any observable, right, any expectation value will be written in this way, right? An observable will be written as the path integral over A of that observable, exponential of the action, divided by this, right? We have shown this many times before. I can just put that identity on top and on the bottom, right? And rewrite this as an integral over A observable A exponential of some effective action. That's the first sense in which we'll use effective action, right? We'll use that in many different ways. Effective action, right? And these three numbers that were in front here, they don't depend on the observable, so they all come out and go away from my calculation, right? The main point is that now my effective Lagrangian, let me call it like that, my effective Lagrangian is half of f mu square plus 1 over 2 alpha del mu a mu square. And we call this second part here, let me put a box around this. We call this second part here the gauge fixing Lagrangian, right? This is the gauge fixing term of my Lagrangian. So just pay attention to what I did here, right? I actually managed to get my strategy executed, right? I separated the integral. Notice that here I'm integrating over a mu's in a gauge fixed Lagrangian, right? So there's only a path integral over different configurations. And I took the integral over the copies, right? The equivalent physical configurations, right? Outside, just like I wanted, right? I took it as a multiplicative factor, and we know what happens with multiplicative factors, right? And that was the same as just what some people do it like that. It's not very general, right? Because it's hard to generalize this for non-abelian theories and all, but you could just say, well, I'll modify my original Lagrangian, adding a gauge fixing term, and you get to the same place, right? Because now I'll do the path integral here, just using here, right? Just using the gauge fixed version of the Lagrangian. Right? But now you can see that it can be obtained from the original theory without making any changes, right? If I say I'm modifying the Lagrangian by putting this term, you could say, wow, you're putting a gauge fixing term, right? You're not changing the classical theory, but maybe you're changing the quantum theory, right? But in this case, I have shown that I didn't, right? I actually just put identities in here, right? The one assumption that should be taken with a grain of salt, because it will not always be true, is this one, right? Because some theories have anomalous symmetries, and anomalous means it will be a symmetry of the classical theory but not of the quantum theory, right? But that's a subject for a more advanced course. Now that we have this Lagrangian, we can go ahead and get the photon propagator, right? So I can write this effective action, right, using the effective Lagrangian, and do the integral by parts, right, without too much worries now, since I am in the Euclidean space, right, to rewrite this as minus half of a mu delta mu, the second derivative, del mu del nu, A nu, right? This is what we already had before. It's just what you get by integrating this by parts, right? And now I want to do the same here. I want to put the two derivatives in one of the fields, right? And what I get doing that is just 1 over 2 alpha a mu del mu del nu a nu. So that's the nu part, right? It's the gauge fixing part, and we'll contribute this small contribution here to the operator, right? Which we can now write. We can write the whole thing as half of d4x, right? A mu of x, and here comes the operator I need to invert, minus del mu nu, second derivative, plus, and then I can put this part and this one together, will be 1 minus 1 over alpha, right? I think all signs are okay here. Minus 1 over alpha del mu del nu, which acts on a nu of x. And the point of this whole thing is that now this operator that is appearing here is now invertible. I can find the inverse for this guy, right? And that inverse is what I call the photon propagator, or beta is the photon propagator G, right? And I'll put a 0 here to remember that I'm in the free theory, right? There's no interaction here, is all Gaussian terms, right? And it is the photon because we have seen before. We know this thing has spin 1, right? It transforms as a vector. We know that the classical equations of motion for this field are the Maxwell equations, right? So we're quantizing the photon field without charges, right? We didn't put any interaction, so there is no electric interaction yet, right? That will come later. We'll do it eventually, right? It's easy to see. It comes from that covariant derivative I talked about when I was introducing this field, right? So I'll call this operator is of course the inverse of the propagator, so I'll baptize this G minus 1 of x, right? And to find the inverse is easier to actually see the inverse of this operator if we go to momentum space. So I'll rewrite the effective action, making the Fourier transform of these two fields, right? So this will become half of d for x, right? This guy will become d for k over 2 pi to the 4th times a mu k, right? A mu tilde of k, but I'll not be carrying the tilde, right? Exponential of I k x. Right, just copy the operator. Remove the box here. Right, and this guy becomes an integral in d for k prime over 2 pi to the 4th a nu of k prime exponential of I k prime x. Right, so I moved the two fields to momentum space. Now I can act with this operator. I'll shift the integrals around a little bit. Let me copy the half. Let me copy this over here and that too, right? And this operator, when I act, right, these derivatives act on x to the right here, right? And that takes down powers of I k prime. That means that this operator will just become, right? In any case, there's two derivatives here, two derivatives there. So I comes down twice. That changes the signs here. And other than that, it's just k prime, right? So this second derivative becomes k prime square. This one becomes k prime mu. This one becomes k prime nu. Once I do that, right, these exponentials, these two exponentials here, can be integrated using d4x right there, right? That's just 2 pi to the 4th Dirac delta of k plus k prime, right? So I can do the integral in x using the exponentials. Let me make a little bit more space here because the only two things missing are the field here and this field that goes here, right? So that's what I get. I already got rid of the integral in x. Now I can do the integral in, say, k prime. Right? It's very easy to do the integral in k prime because I can use this delta, right? So I just copy this guy. These powers of 2 pi go away, and I'll do the integral in k prime. So this I just copy down here. And actually, let me do the integral in k just to keep, it doesn't matter, but I want to keep consistency with my lecture notes. So I did the integral in k, and then I just call k prime k. That means I'll exchange k. Let me do this clearly. Let's keep k prime here. I just exchange k by minus k prime, because that's what this delta does. And I do not change anything over here, right? Just copy everything else because k was only here. Right? And then I remove the prime because that's just a name. That keeps the notation consistent with my notes. Okay, somehow I lost a power 4 here. And this is it, right? This is what I wanted. And this is now the propagator, the inverse of the propagator in momentum space, right? This is the inverse of the propagator in momentum, which is much easier to see what it should be, right? I just have to find a G that satisfies this equation. G mu rho of 0, K should be delta mu rho, right? And that's easy to write straight away and test, right? This is G mu of 0, K, just 1 over K square delta mu minus 1 minus alpha K nu over K square. And let me put a box around it because this is the photon propagator in Euclidean momentum space, right? And you see now that the expression for this propagator depends on this alpha, right? Which is related in a fairly complicated way to the gauge fixing condition, right? In fact, this in many places and in many people actually call this a gauge fixing. For each value or alpha, you have a different fixing of the gauge. In fact, alpha equals 1, for instance, is called the Feynman gauge, right? The important thing is to not confuse this with this, right? Each of them is in its own way a gauge fixing, but you should not confuse one with the other, right? The important thing to notice is that what we did was to impose this condition and then do a path integral over C, right? We did integrate over C in a Gaussian way. So that what we're doing is imposing this condition for different values of C on a distribution that the width is given by alpha, which the width is given by alpha. Right? So it's a complicated way of fixing the gauge, but it is the way that is equivalent to putting a gauge fixing term in the Lagrangian, right? And this is a very popular gauge. It's useful for many things, but it's just one of many gauges. In the end, your final observable should be independent of the gauge fixing condition, but this is very popular because the propagator, of course, becomes very simple in this gauge. Well, let me write it like that so you don't forget that it's specific for this gauge is just k square delta mu nu, which makes very obvious that this thing has a pole for k square equals 0, so that's a massless particle, right? That's the photon. Again, that's the photon propagator right there. With that in mind, we can now make a summary of the new fine rules that we got for the photon, right? So this is the one I just shown, right? The one for the Euclidean space in momentum, right? If you rotate back to Minkowski, that's how it looks, right? The important things to notice here is, again, we're talking about bosons. You see the momenta the direction of the momenta does not matter anymore, right? So I'm not using an arrow to indicate particle and antiparticle. This is a real field, so it is its own antiparticle, right? And since the photon propagator involves two Lorentz indexes, right, it's easy to see that the vertices that are at the edges here will have to be labeled by some Lorentz index, right? So that's the mu and nu that I indicated here, right? As for the external legs, right, we can do a heuristic approach like we did with the fermions, right? And see that any initial state will have to be annihilated by a field, right? For the field operator acting on the vertex, right? So any incoming photon will have to be annihilated at a vertex and then continue to whatever interaction we propose, right? And that field carries an index nu. And if I apply this field here, the annihilation part will give me this, right? The exponential, we know what the exponential does. It participates in the momentum conservation for that vertex. But now we have this function, which serves, right? This is complete analogy with the u and v functions that appeared when I did the same for the fermions, right? The epsilon now carries the polarization information for that incoming photon. The same for the outgoing photon. So any outgoing photon, I have to specify the polarization. It is created at a vertex by this field. And when you contract it to the left, right, you match the creation part of this operator to this, right? You get this exponential and the complex conjugate of the polarization, which, by the way, we have been using real polarization. I assume epsilon, the polarization was real, right? Which is very useful if you're talking about orthogonal polarizations, transverse polarizations in, say, x and y direction. But sometimes you will know, right? Like in electromagnetism. Sometimes you want clockwise polarizations that evolve in time in a clockwise or anti-clockwise manner. And in that case, it's better to use a complex polarization. So this is the most general thing. You get a epsilon star here, right? And then that gives me the rules for the external legs of photon, right? So external leg will always come together with the polarization, which has an index again for the vertex, right? So you know that the vertex here has a field, a mu, right? And that's the index that shows up here. It can be contracted with other things. I still didn't talk about this interaction, right? The one I'm drawing here is the electromagnetic one, but it could be any interaction. You always must have a field there to annihilate the incoming photon. So there's an index, a Lorentz index for the vertex, right? And of course the momenta, and this is for the outgoing photon, you get epsilon star, right? If your polarization is complex, otherwise you can forget this star. Right? So this is all of it for today, and this is an important milestone for the course, because now we quantize all the fields we wanted, right? Spin 0, spin half, and spin 1. We won't go higher than that in this course, right? Although it's possible to do quantization of higher spin fields, right? But now we have all the fields we want to work with, right? And that's it for today. See you next video, and we'll see where we go next.